Good day. Today we're going to be giving the final presentation for Spartech Supermileage. We will be going through an introduction and going through the engine development, sensors and telemetry, wheels and brakes, body and chassis, and sales and social media. Spartech Supermileage is a project that helps students apply their knowledge to a real-life problem. Our goal is to compete in the size supermileage competition by having a vehicle which is fuel efficient and weighs the least amount of miles per gallon to be able to win the competition. At the moment, we have already submitted the design report and also given the virtual presentation, and we have also completed the fast track deadline.
Regarding the vehicle, the chassis mainframe and wheels are made of carbon fiber. For the dimensions of the vehicle, it has 2.5 meters long, 355 millimeters width. For the height, including the wheels, is 814 millimeters, and without the wheels, 606 millimeters. It has a ride height of 208 millimeters. The shell will be made out of fiberglass. It has 3 windows and we will use clamps to mechanically attach it to the chassis.
This is the engine we chose for the powertrain of the car. It is the Predator 212cc model and it has these specs. Hello, my name is Ricardo Bocachica and I'm going to be presenting the engine modifications in which we can find the manufacturer connecting rod and the manufacturer engine jig. This engine assembly is in an undergoing process which we are going to receive the modification soon in order to test the engine and put it in the chassis. This time we have the camshaft modification that we needed to extend in order to synchronize the time of the valves with the output of the engine, since we had a CVT in the output of the engine. For the transmission, we decided to use a CVT to obtain a range of approximately 11213 configuration, which is gonna provide us a range of gear ratio to maintain the desired fuel efficiency. It can be connected in both of these ways with a uh, jack shaft and without the jack shaft, but we are going to connect it without the jack shaft in order to be a direct transmission. For the starter, we chose a model that fitted the Predator 212 engine, which is the engine that we are using. It works with a 12 volts battery. It has a key ignition and includes a kill switch for safety purposes. Hello, my name is Ricardo Bocachica, and I'm going to be presenting to you the performance during the competition using track analysis. We analyze the track geometry in order to establish in which track parts we are going to be in a downhill or uphill position. And using this, we did a free body diagram considering the forces of weight, the normal force, the rolling resistance, and the aerodynamic resistance to calculate the traction force using the formulas that are listed below the photo of the free body diagrams. For the formulas, we use the minimum and maximum velocity allowed in the competition in order to establish a range of operation of traction force in each track part. And using this value, we were able to calculate also the wheel torque in each track part. Using the wheel torque, the gear ratio, and an assumed efficiency of transmission, we were able to calculate the engine torque necessary for each track course. And with this value and the velocity of the car and the distance of the track course, we were able to establish the engine power necessary for each track course. We also used a performance simulator in order to obtain data in Ricardo Wave with the parameters listed in the left to obtain the graphs on the right. Now we use the modified engine specs in which we reduce displacement and lower the fuel consumption, obtaining the graphs on the right. Compiling the data of the stock engine and modified engine, in the indicator RPM the torque of the stock engine was 15 foot-pounds and in the modified engine was 4 foot-pounds. In the power of the stock engine we have 7 horsepower and in the modified engine we have 2 horsepower. This shows indeed that the car will be able to move with the 300 pounds that it has, comparing the data to the track analysis.
Good afternoon, my name is Carlos S. Rodriguez Quintero, and today I'll be explaining the dynamometer system and how it functions. It was created to get experimental data and validate simulations of the engine. The system takes the output power of the engine and transfers it through a pulley connected to a shaft which rotates. This shaft contains a brake disc that interacts with a brake caliper. The brake caliper extends the brake torque through a brake arm that transfers a force that will be detected by the strain gauge. This is called the brake force. Here we can see the data obtained by the system. The value shown is a simplified representation of the raw values obtained. We were able to obtain the stock engine's horsepower relative to the engine speed at a constant torque caused by a constant brake load. Here are some views of the dynamometer system.
So, small update in the electronic side of things. The previous EFI system, comprised of the Arduino Uno and the Raspberry Pi 4, was scrapped for a new one developed by a local tuning shop called Alpha X. This new EFI system is basically plug and play. As soon as the system is installed, it will be connected to an independent O2 sensor so that we can dial in the fuel and ignition maps for better efficiency. Besides already being developed and ready to install, the new EFI system has many features which make it a viable alternative. Firstly, the system has electronic ignition timing and fuel injection, which open the window for a more precise control of the combustion process. Also, the EFI system includes all the necessary sensors for it to work, meaning we only have to install it and tune it for the purposes of efficiency. The telemetry data from the EFI system will be sent from the ECU to the Raspberry Pi via USB. The Raspberry Pi will then take said data and display it on a screen located inside the cockpit for the driver to use.
Now we're going to talk about a little bit of the pieces that have been manufactured and are mainly used for the steering system. In this slide, we can see the CAD designs that were going to be used to manufacture some pieces for the car. On the top left, we have the front axles that were going to be manufactured. On the bottom left, we have the tie rods that are going to be used in the steering system. And on the right side of the screen, we have the result of the manufacturing process of these both parts. We have the tie rods and the front axles. Both of them work with threads and are going to be knotted on each side of the wheel. On the left side of this slide, we can see the CAD design of the rear axle that was going to be manufactured for the car. On the right side, we have the result of the manufacturing process of the rear axle that is going to be mounted on the rear wheel of the car. In this slide, we have a picture of the joints that were manufactured. These joints are going to have bearings on top and on the bottom, and that's the bearing that they are going to be used on the right side of the screen. These two joints are going to be the pivot points that the pivot part of the car are going to pivot in. We have two pivot points in one on each front wheel, on the front left and front right. In this slide, we have a part that is going to work with a bearing tube. This part is a flash mount. This flash mount is going to work with the bearing tube and permit the steering shaft to pivot in a point. This is also going to be mounted with a triangle in the anchor mount system that is going to let the car steer. Here we have the rear axle adapters and the pitman arm. The rear axle adapters are the two tubes that are on the left side of the screen. These adapters were meant to work with two carbon fiber tubes that were slightly angled of 4 degrees. These adapters are bent likewise to correct the angle, and in those two holes is where the rear axle is going to be in. On the right side of the screen we have the pitman arm. This arm is going to be adapted to the steering shaft and work for the steering system in this car.
Greetings, my name is Sebastian Diaz Reyes, and today I will be talking about the body and chassis. For the analysis performed on the chassis mainframe, it was performed using ANSYS ACP to generate the carbon fiber composite data and then transferred to a static structural approach. As for the mainframe, a force of 200 pounds was applied on the seat. For the inverse reserve factor, the result was 0.65 on a maximum, which will be equivalent to a 1.54 safety factor. The areas that require reinforcement were the tubes holding the seat, both back steering tubes, chassis support tube, and both chassis support joints. As part of the competition, a roll hoop test will be performed applying 250 pounds on different directions of the roll hoop. In order for a roll hoop to withstand these forces, a reinforcement was applied with the geometry shown in the figure. After the reinforcement, the roll hoop will safely withstand the forces of this test with an inverse reserve factor of 0.83 as a maximum. On the following pictures, we can see the chassis frame and its assembly including the wheels, steering, and the driver's seat. As for the shell, it is being manufactured in three phases. The first one is manufacturing the shell nose mold seen in the figure on the right. For the middle part, we will be using a polycarbonate sheet, and for the tail and final phase, we will be using a mold as well. In the figure on the left, we can see the prototype of the finished shell.
Next up, we're going to start talking about the braking system of the car, the braking lights, and everything that has to do with how the car operates while rolling and braking. In this slide, we have some of the components that are going to be used for the braking system of the car. We have the braking light that is going to be detecting the car is slowing down and is going to light up. We have the brake pressure switch, the Magna MTL sticks brakes. This is going to work on the front side of the car with the two discs and the wheels. We had a female T-junction aluminum fitting that is going to work for the hoses and the lines of the braking system, and the caliper mount adapter that is going to be mounted on the pivot joints of the front wheels.
Here we present our running gear. As you seen on the frame assembly photo, our vehicle has 3 wheels. In the upper left image, you can see the bike rim used. In the upper right part, the wheel model. In the bottom left part, the rear wheel assembly, which is adjusted to the chassis with 2 nuts on both sides. On the other hand, in the bottom right area, you can see how our tires were assembled, using the tubeless wheels method. Finally, in the center photo, you can see the front wheel assembly, which includes the steering knuckle, the brake and brake adapter, the disc, and the wheel. This is the vehicle steering system, which is based on the Ackerman model. In the first image, we can see the CAD of the system, and in the second image, we can see the current steering system. All the steering is in aluminum, except for the steering wheel that is 3D printed.
During the course of this semester, the non-technical division had various fundraising activities to raise funds to be able to achieve all these goals. Between them, they had frappe sales, pizza sales, bandana sales, a car wash, and a pantalla sale. On the other hand, our outreach or publicity division focused on our platforms on social media, which are Instagram, Facebook, and LinkedIn, which our outreach base is based on Puerto Rico and the United States. Sales, we mostly have content on sales promotion, team exposition, member highlights, and these has raised around night. Our outreach has been expanding through all our social media during this semester. Thank you for your attention. Any questions?